Hello, we are Team 26022, Coral Reef Arks Hydrodynamics. We are working with the University of Arizona's Biosphere 2 to design and build coral reef arks, which help stimulate coral growth. Welcome to our Design Day video.
Coral reefs are biodiversity hubs teeming with life. They provide shelter for marine life, and in doing so, they are providing a massive food chain that extends all the way to us. Not only that, they protect coastlines from storm damage by absorbing wave energy and add almost $10 trillion a year to the global economy. But we are experiencing a crisis right now. Worldwide, coral reefs are declining at an alarming rate. 50% of coral reefs have been lost in the last 50 years, and if nothing is done, we could lose 90% of them by 2050. We are combating that decline by working with the Holome Arks initiative and Biosphere 2 to develop designs for coral reef arks, which are artificial floating coral habitats. These arks consist of a frame with panel attachments for the coral, feature other subsystems, and are typically deployed in the ocean long term. Our project was broken into two parts. The first, focusing on hydrodynamics of coral panel configurations for a 2V arc frame, and the second, focusing on hydrodynamics of different frame geometries and building of that system.
We selected three potential panel configurations: frame-centered, hub-centered, and face infill. The panel configurations were modeled in SolidWorks and analyzed using computational fluid dynamics in ANSYS Discovery. Discovery is a fast simulation tool that's especially good at visualizing how flow moves through complex geometries. It lets us quickly compare how each panel layout redirected water through the arc. The key metric we were evaluating was flow attenuation, basically how much each design shields the corals from the current. For the corals to get adequate nutrient cycling and gas exchange without being damaged by high-speed flow, we needed that attenuation to land between 20 and 70%. Alongside the CFD, we also conducted wind tunnel testing on physical scale models to validate the simulation results. We built two models for this, a bare frame and a frame with the frame-centered panels attached.
Our original plan was to use 3D printing to create our models for wind tunnel testing. The 2V bare frame was successfully printed, however we were unable to print the configurations with panels. We pivoted to constructing a 2V frame with frame-centered panels out of steel rods, 3D printed hubs, and 3D printed panels, which we then assembled using epoxy. The wind tunnel testing involved mounting both the bare and frame-centered models onto a force balance before running flow over the models. This produced drag and moment data that was compared with the simulation results from the CFD. Once the CFD was verified, the problems of proper panel placement and frame design were tackled. From the results of the CFD and the validation from the wind tunnel testing, we concluded that the frame-centered panels were the optimal configuration. We developed a prototype and delivered fabrication instructions for the panels to the Biosphere at the end of the semester. These panels were then installed with coral fragments on the 2V arc that had been deployed in the Biosphere 2 ocean.
Once we determined the optimal panel configuration, we transitioned to evaluating three frame geometries. The three geometries we tested were a 2V geodesic sphere, a 1V geodesic sphere, both of which had been previously used for arcs, and a truncated octahedron. New panels were designed for each geometry in order to keep the coral area uniform throughout the designs.
With the panel configuration locked in, we moved into the second phase, picking the right frame geometry. This time we needed reliable quantitative numbers, not just visual comparisons. So we stepped up from ANSYS Discovery to ANSYS Fluent, a higher fidelity solver. But before we trusted Fluent with design decisions, we validated it. We ran Fluent on same scaled models we'd already tested in the wind tunnel, same geometries, same flow conditions, and compared directly. Fluent matched the wind tunnel data with a 99.5 correlation. It was tracking physical reality almost exactly. With that confidence, we ran the three candidate geometries at full scale across three operating speeds, from calm flow to storm-like conditions. The 1V geodesic sphere came in overshielded at about 59%. Too much blocking which risks starving the corals of nutrients. The 2V frame-centered came in undershielded at about 46%. Not enough protection during high-speed events. The truncated octahedron landed right in the middle at 51%, the biological sweet spot for nutrient and oxygen exchange. It also offered better load distribution and easier arms installation. That's the design in the water at Biosphere 2 today.
Once we selected our geometry, we finalized the designs for the subsystems, which included the arc frame, the coral panels, the autonomous reef monitoring structure, the suspension and mooring, and a strain gauge assembly. This also allowed us to begin fabrication.
For the Ark frame, PVC struts were cut and sanded in order to fit into the 3D printed PLA hubs. Once the struts were prepared, we began assembling. During this time, Dyneema rope was attached to 4 points of the frame for the suspension lines. The frame was left to cure and harden for a week prior to deployment, and it was secured with bungee cords to ensure it was kept in compression. The coral panels were fabricated from HDPE sheets, and our design included 33 panels. The panels have ceramic tiles for coral attachment, and they are fixed to the frame using U-bolts. The panels are attached to the top portion of the frame to ensure that the coral receives adequate light. The autonomous reef monitoring structure, or ARMS, consists of several layers of PVC that are seated on the ocean floor for several weeks or months before Ark attachment. This is done to collect different microorganisms that are necessary to sustain a full coral ecosystem inside the Ark. The arms consist of layering plates, cross spacers, and nylon spacers. The layering plates and cross spacers were cut out of sheets of expanded PVC, and fabrication was simply stacking and bolting these on top of each other. The suspension and mooring consists of Dyneema rope, 3/16 steel shackles, buoys, and sponsor-provided anchors. There are multiple Dyneema ropes at the top and bottom to distribute the forces across the frame and the anchors it's attached to. There are also 3 buoys attached to the frame in order to maintain the Ark's buoyancy and stability. The instrumentation included in our system consists of a Lycor 193 to measure coral light exposure and a modular strain gauge to monitor coral growth over time. The strain gauge can be used on multiple arcs and attaches to the bottom portion of the suspension.
Once all of our subsystems were constructed and tested, we were ready to deploy the Ark. We removed the bungee cords from the solidified Ark and added the coral panels to the top 3 layers of struts and mounted the arms on the bottom of the frame. After the frame was in the water, the suspension system was first connected to the anchoring system and then to the frame. 3 buoys were then attached to the horizontal crossbars at square faces to increase stability and buoyancy. The entire system was successfully deployed. For the next iteration, we will be spray painting the Ark frame pink and purple to provide additional UV protection and resembles coralline algae, an organism that provides structural stability to coral reefs. Spray painting the Ark could also be tested to see if it has any effect on long-term coral growth. In terms of large-scale production, PVC is a versatile material and holds up well underwater, but small amounts of harmful microplastics could still leach off over time, creating an issue in itself. Future Arks to come could be constructed out of wood or bamboo that's been treated with a marine-grade wood sealer in order to use biodegradable materials and increase the sustainability of the project. In addition, the geometry we selected, the truncated octahedron, is a viable option for an arc wall due to natural tessellation, meaning we could piece together coral arcs like a puzzle to absorb and disperse wave energy during storms, a characteristic of natural coral reefs. Our project is about testing and evaluating designs for coral arcs. We designed and tested panels for the coral, moved into full arc designs, selected a frame configuration, and we deployed a finished product in the Biosphere 2 ocean. Now our Ark can be used in research to develop strategies for coral arcs in the wild to combat the worldwide decline of coral reefs, a critical part of Biosphere 1.